Hello, everyone, and welcome to our Algorithms and Data Structures lecture today. Today is, as you can see, our last lecture because we're advancing rapidly with the content. Last week, we discussed selected topics. In particular, we looked at two selected algorithms, one for the fast matrix multiplication, and the other one is the fast inverse square root. Chapters 1 to 8 are typically topics discussed in a normal algorithms and data structures class. Obviously, I'm setting, my own specialty and focus on the course as I consider it necessary. Then in a typical algorithms and data structures course, there would be some selected algorithms. However, today we will talk about quantum computing, and this is something you will probably not find in most other introductory courses to algorithms and data structures. And it's more like an outlook. Concretely, we will today discuss an introduction to quantum computing. A traditional computer deals with bits. We will look at qubits, which are quantum bits. And then we'll look at quantum logic gates, quantum computers, and quantum algorithms. And quantum computers come with the potential to solve certain algorithm problems, not just faster, but in a better complexity class. And that's why I think this is super important, actually, to an algorithms and data structures course, even though the topic is evolving and large-scale applications are still challenging. But all of this will change in the coming years and decades. And that's why I want to prepare you a little bit for that quantum future. And we'll look at quantum computers. We see what they're useful for, but we will also see some challenges and what quantum computers are definitely not. So we will separate hype from reality. And I think this will be a good addition to what we have done so far, because it's more like an outlook, and we will get back also to complexity. In order to understand this course or this class, what you need is complex numbers, but this is something you have all learned in your maths course. A complex number extends the real numbers. The set of real numbers is extended, and a complex number has a real number plus b times I, where b is a real number and I is an imaginary number. And I squared is -1. So this is something that you cannot do with real numbers, because if you square a number, a real number, you will always get a positive number or 0 and not something negative. Complex numbers are necessary for doing quantum computing, and you also need a background in logic gates, like and or not. But this is something you also know from your introduction to computer science. And we will now use this as a basis in order to introduce quantum computing. So what is actually quantum computing about? There is lots of hype, but also lots of nonsense that I read on the news. Though quantum computers are not supercomputers, they will not replace today's computers as a whole, but they address a certain niche, and for that niche, they show lots of potential. So in quantum computing, we want to take advantage of quantum mechanical phenomena in order to perform computations. And such computers that would allow us to do quantum computations are known as quantum computers. And now the question is, what are quantum computers useful for? Well, they take advantage of quantum mechanical phenomena, and in order to describe them, we need complex numbers. And quantum computers are helpful for a certain class of computational problems. And for that certain class of computational problems, quantum computers, where there are some quantum algorithms that would solve this problem in a better complexity class. And then we would get a quantum speedup, and it's not just, a constant speedup, but actually a better complexity class. But there is a limited number of quantum computers available. There's a limited number of quantum algorithms. So all of that isn't that straightforward. And we'll discuss this today and see why that is so challenging. But the great thing is quantum computers are inherently parallel, and they take advantage of quantum parallelism, and this gives us a major speed up in certain settings, as we will see later. And this field, the field of quantum computing goes back to the 1980s. In the last few years, we started to have more quantum computers available, yet limited, but we're making progress. So this field got more attention in the last few years, in particular applications to machine learning or encryption, decryption problems. For example, to crack today's encryption methods, as well as maybe to speed up machine learning or to learn better patterns from less data. There are such applications, but we'll see more applications of all of this later. But there's a lot of, rumors what quantum computers could be. I read in the news that quantum computers would replace all of our computers and we would only have quantum computers in the future. Well, not so soon, and probably that would be quite far away. What I think will happen in the coming decades is that we will have hopefully better quantum computers that have more qubits, and maybe we have more quantum algorithms that work, and then quantum computers would address a certain niche of computational problems. But in the foreseeable future, we will still use our traditional computers, which are often a combination of RISC-CISC architectures. This is something we will probably be using for mainstream computing for the foreseeable future, with some branches to quantum computing and maybe more of them in the coming decades. And you're just at the beginning of your career, so it's something very exciting that will evolve as you keep progressing with your career. And hopefully there'll be more quantum computing applications. And today you will get the framework in order to understand what all of this is about, so you can follow up the developments in the coming years and decades. In traditional computers, we have bits, and the bit is either 0 or 1, and a qubit or quantum bit is something different. It's a quantum mechanical version of a bit, and it actually can be in both states at the same time. So it can be in 0 and 1 at the same time. And that's something we call a so-called superposition, that our qubit is in both states at the same time or simultaneously. And this property of superposition actually gives us a parallelization. I am in 0 with a certain proportion and in 1 with a certain proportion. So that's a parallelism. And now imagine I have like 10 qubits combined. And if I have like 10 bits combined, I would be in one state with 10 traditional bits. But with a qubit, if I have 10 qubits, I can be in 2 to the 10, so 1024 states at the same time. And this leads to a massive parallelization, and then using the right algorithms and having the right hardware at hand, this can give us a massive speed up. Ideally, maybe for an optimization problem where we would have to try each possible solution at a time. So we look at one possible solution, then the next possible solution, and so forth. We would maybe need exponentially much time to solve a certain combinatorial problem. But with a quantum computer, maybe we could look at all possible solutions at the same time and then find out which of those solutions is actually the solution, or which of the candidates is the actual solution. So theoretically, we could get with this approach an exponential speed up, provided we have the right hardware and we have the right algorithm, but that's more challenging. And we can also define qubits in a mathematical way, and this is something I will show now on the whiteboard. So screen share is appearing now. So we will have a qubit, and a qubit is denoted in something like this. And this notation here is something we call a ket, because there's the bra-ket notation in physics that is used in quantum mechanics. And this is a ket. Bra is the other one, and the bra would look like something like this. But we only care about the kets today because the bra-ket notation allows us to address this. But we only care about the ket for now, and we say a ket, this is our qubit, and our qubit needs, or we say it's in the state 0, and it's also in the state 1 at the same time. And in order to describe now how much it is in 0 ket, as well as how much it's in 1 ket, I introduce two so-called probability amplitudes. So I have alpha and beta. These are called probability amplitudes. And this is where the complex numbers come into play, because they are complex probability amplitudes. So alpha and beta are complex numbers. And we can also re-express this because so alpha ket is a vector eventually, and 0 ket and 1 ket are vectors too. So we could describe this in a slightly different way. So I have my alpha and beta. And my 0 ket is something I can write as 1, 0. So this here means it has a 1 in the first entry, which refers to the 0 component. And the 1 ket looks something like this, as 1, 0. Where this one here refers to the 1 component. And now I can, I have these vectors 1, 0 and 0, 1, and I have these factors alpha and beta, and I could also just re-express this qubit as something like this. So I just multiply those factors and I add it. This is called a qubit. And now there is a certain constraint on alpha and beta. So we said it's complex probability amplitudes. So it's a proportion of how much our qubit is in 0 and how much in 1. And there is a clear constraint. So if you remember complex numbers, you can take their modulus or absolute value, and the modulus, so the absolute value of alpha squared, plus the modulus of beta squared, this needs to be 1. So this is super important that these are this constraint is followed, otherwise you don't have a valid qubit. This doesn't come from computer science, this comes from quantum mechanics. And in quantum mechanics, you can look at states that not just have 2 entries, but more entries. And this constraint here is just a consequence of the more general constraint of such vectors in higher dimensions. But here we have just, reduced this to 2 entries, and then these are qubits. But it comes from much more general description in physics. And one valid state could be, for example, something like this, where I say my alpha ket is, for example, 0.6 and 0.8. Remember, these are now complex numbers, but these complex numbers only have a real part, no imaginary part. And then this is my alpha, this is my beta. And if I square alpha, so 0.6 squared is 0.36. So we can write this out. Alpha squared is 0.36. 0.36, and my beta is 0.8, and beta squared is 0.64. And just that we are working concretely with complex numbers, I've just put the modulus around it, because there could be also an imaginary part, not just a real part. So this a cat would be a valid qubit. And what we need next in our framework is now we need to be able to manipulate such qubits. When you work with traditional binary bits, so just bits that are either 0 or 1, we have fundamental logic gates. So classic logic gates in binary, so logic gates would be and or not in classical binary. And from those, you can build more complex ones. And what we need now are some gates that allow us to deal with qubits. So we need quantum logic gates. And these logic gates that we use in the quantum world, they are different. And they are expressed also in a different format than what you're used to. There is the simplest quantum logic gate that actually makes a change that you can imagine. It's called the X or just NOT gate. So there's also a NOT gate, it's often called X. And what it does is it's the quantum equivalent of the binary NOT gate. The binary NOT gate flips you a 0 to 1 or a 1 to 0. And the quantum one, eventually, it will just flip these amplitudes that we have up here. And we can say, for example, if I have my qubit that is say alpha and beta again. So alpha is 0 cat, or alpha times 0 cat plus beta times 1 cat. This is my qubit. And now I say I apply my NOT operation to this qubit. What I will get eventually is I'm just flipping alpha and beta. So I have my 0 cat plus 1 cat. And this is now the beta, and here's the alpha. So we have just flipped them. This is what the NOT gate does. The interesting thing is you can represent these quantum logic gates as a matrix. And matrix representations are super helpful to describe all of this. So we have a matrix representation of the X gate. And this would look something like X is a matrix that looks something like this. And I'll show you why this actually makes sense, because I have my X, which is the matrix, and I multiply my vector. Remember, we can describe a qubit also as this vector, first entry alpha, then beta. We have seen a valid qubit here. We can take our matrix and we can multiply from the right our vector. We can say 0.608, this was our valid qubit, and you can multiply this with X. We can write this out. So X is this matrix, and this is our vector, this is our valid qubit. And now you're tasked with doing this matrix vector multiplication. And once you have the result, send it to the chat, please. So it's just simple linear algebra for now. Do you all feel okay with such multiplications? Maybe just thumbs up, thumbs down. We got a few answers now. Well, I asked for an update, and it is eventually just 0.8, 0.6. So we see with this matrix representation, we can just flip alpha and beta, and this is what our quantum logic NOT gate does. Before, I've defined it here as a function, and now we've seen it down here that we can actually express such a gate as a matrix. And there are many other gates available. We have this NOT. There is not like a classic AND or. There are other fundamental gates. I'll just show you one more for now. And what I said to you is we're taking advantage of the superposition in quantum computing because this gives us parallelism. But when you have your quantum computer, so you have a quantum system that is somehow isolated from the outside world, because a quantum system needs to be isolated, otherwise it starts to interact with the classical world. But somewhere from outside, I need to be able to access my quantum computer. And in the outside world, I have binary information that I put into the quantum computer. And so I could say, for example, I'm starting with a qubit that is only 1 in state 0 and 0 in state 1. So it would be like a qubit that looks like a classical bit. And somehow I need to be able to create a superposition. And because I need the superpositions to take advantage of quantum parallelism, and then I take more gates to work on my quantum state. But somehow I need to be able to create all of this. And that's why the next gate is called the Hadamard gate. Hadamard gate. And the Hadamard gate has actually some task. What I want is, if I have a basis state like 0 ket, which you remember, 0 ket is just 1, 0. I actually want to create a superposition from that because the 0 ket is not a superposition. So what I want is to create, so I want to map this to something that would look like a 0 ket plus a 1 ket, but now I still need some alpha and beta. And if I want a so-called equal superposition, so I write this here, I want an equal superposition. So I want this to be equally in 0 and equally in 1. What would you try? Maybe without looking at the slides. What would you put here as an alpha, and what would you put there as a beta so that you're equally in 0 ket and equally in 1 ket? If you have any idea, maybe a thumbs up or a thumbs down if you don't have an idea about this. And if you have any guess, maybe just turn on your microphone or we got a thumbs up, and put this in the chat.
Maybe
got
an identity
yeah.
matrix?
I can hear you.
Maybe an identity matrix or not?
Well, alpha and beta are complex numbers. They are not a matrix.
Yeah, okay.
Fine, it's okay. Like one student suggested, we could put 0.5 and 0.5 here. This would look like most obvious that I could put there 0.5 and 0.5. But now, remember, this must be a complex number. And if I go back to my constraint up here, my constraint was I take the modulus of alpha and square it, and the modulus of beta and I square must be 1. And now if my alpha is 0.5 and I take its modulus, it's 0.5 and I square it, so it's 0.25. And this here as well, so this 2 would add up to 0.5 eventually. So not a valid qubit. So this is not valid. That's why we will try again. And one student already suggested this correctly in the chat. we actually need a slightly different change. We would take, for example, I write it a bit different than what the student wrote in the chat. I would take for alpha and beta my pen just stopped working. No. I could take, for example, something like this. 1 divided by the square root of 2 and 1 divided by the square root of 2. This is one way how we could do it, because if you take the 1 divided by square root and you take its modulus, it's still 1 divided by the square root of 2, but we need to square the modulus. And if I have, just as a side note, 1 divided by the square root of 2, and I square this, so I square this will be 1 divided by the square root of 2 times 1 divided by the square root of 2, which would be just a half. And that means this actually leads to a half. So I have this modulus squared a half and this modulus squared a half. And then I finally have a valid qubit. So one student in the chat suggested something slightly different. The suggestion was the square root of a half. And if we re-express this, say the square root, the student wrote the square root of 0.5, so the square root of a half, that means the square root of 1 divided by the square root of 2. That's 1 divided by the square root of 2. So was also fine. In quantum physics, this notation, or as in quantum computing, is preferred that I write 1 divided by the square root of 2 and not the square root of a half. But what you suggested in the chat is also fine. Now, my challenge was, I want to look at this one here again. And so I want to map my my 0 ket to an equal superposition. And just as a note, if you later double check the slides for revision, this notation here is just a little bit shortened in the slides, because I say it's 0 ket plus 1 ket. Great. And I divide this by the square root of 2. But this is what the slides say, but this is just, I add the 0 ket and the 1 ket, and then I have this denominator, square root of 2. So it's just the same. It just looks a little bit smaller, or it's more compressed. And in order to create this superposition from 0 ket, I need the Harder-Matt matrix, which refers to the Harder-Matt gate. And it actually looks something like this. And this matrix, if you try this matrix, say H times our qubit, say 0 ket. So I multiply 0, well, just move this a bit closer, that I have 0 ket. I would just write it like this. This would mean that I have the 0 ket, which is 1, 0, and I multiply this with the Harder-Matt matrix, 1, 1, 1, minus 1. What we would get eventually is I would have a 1, 1, because just multiply this column and this row and the column and this row. I would get this as a qubit, but this qubit is again not fitting our constraint, because we have this constraint here, because 1 and 1 would add up to 2. So I need to put something in front of the matrix, and what I put in front is a normalizer, and the normalizer is 1 divided by the square root of 2, which you could write for every entry in the matrix, but it doesn't look too great. So we just put this actually in front as a constant factor of the matrix. And then we would keep this, and this is just the equal superposition from before, because we could say this is 1 divided by the square root of 2 times the 0 ket plus 1 divided by the square root of 2 times the 1 ket. So this was just the equal superposition from here. So this is what we have created. Now you may be wondering, what is this -1 down here useful for? Well, we have turned the 0 ket into an equal superposition. You can also have the 1 ket and turn this into an equal superposition. And the superposition that we would get with the Harder-Matt matrix is the 0 ket minus the 1 ket divided by the square root of 2. Feel free to try this out on your own. You have the 1 ket and you multiply this from the right with the Harder-Matt matrix, and you would get this equal superposition. And then we have a superposition, and then we can actually start doing our actual quantum computations that we are looking for. And this is what we will see now in the slides. So I've just kept a few slides what I have shown you interactively. This was the representation of a qubit, a few notes on quantum logic gates, and here how the NOT gate is defined, what the NOT gate looks like with an example, as well as how to create the equal superposition with the Harder-Matt matrix. What we need next is actually more gates that can do our computations, because we want to start with this equal superposition, and then somehow we need to manipulate the qubits. And what this would look like is something like this. So what I see depicted here is a quantum circuit. And in a quantum circuit, I need to feed something from outside, so from our classic world, from outside into the quantum computer. And this is a qubit 0, 0, 0. I could also feed in ones. So 0 kets, I have 4 qubits feeding in. And then I have some operations in here. They're not specified correctly here, or not in detail. So we have this one here. This is actually a conditional NOT. Doesn't matter for today what a conditional NOT is. And then we have some blocks here that do something. And we have this block here. So maybe some of these blocks, like this one here, is a Harder-Matt gate. So I create some superposition. Maybe this one is a Harder-Matt gate. Maybe this one is a totally different operation that we don't know yet. And eventually, when this progresses, I am updating my quantum states with some operations, whatever the concrete algorithm looks like. And I will then want to finish the computation. And finishing is not the tricky part. Finishing is denoted by such a measurement operation. And you don't need to be an expert in quantum physics, but I'm just curious, who of you has learned some quantum physics before, maybe in high school or something like this? If you have, maybe thumbs up or thumbs down. If you have come across this, so we get a thumbs up. Maybe if you have never come across quantum physics, also send some reaction. Just curious. And you don't need quantum physics for this course, because I'm providing all of this now that we need. And the measurement is an operation that creates something really weird. And why this is the case, this is something we discussed in a quantum computing course in detail. Today, just a brief overview. So we have our qubits, our quantum states. And they have some amplitudes, alpha and beta. And now I want to look at the quantum state, and I want to know what's its alpha, what's its beta. And for this, I need a measurement. And once I measure, the quantum state will collapse into a classical state. So when I measure the quantum state, it will no longer be a quantum state. It will actually turn into a classical state. And if I have a quantum state like before, for example, we had this quantum state here, 0.6 and 0.8. If I measure it, we could guess, because the 0.8 amplitude is bigger than the 0.6, we would rather measure a 1 ket, because it's more in the 1 ket than in the 0 ket. But the measurement is a probabilistic operation. It may return a 1 ket next time I run the experiment. So I need to run the experiment again from scratch, because I have measured, and then the quantum state is gone. It turns into a classic state. If I run the whole experiment again and I measure again, I may get a 1 ket or a 1 again, but I could also get a 0, because it's a probabilistic measurement. And if I have such a state and I measure, I will not always get the 1. I will also sometimes get the 0. And that's why such a quantum experiment is something you cannot just run once. You have to run it multiple times, each time measure when you're done. And then you would sort of, collect these different outcomes, because this is just 1 qubit, but we have 4 qubits in this experiment. And you would eventually sort of record the distribution of your outputs. And if you run the same experiment, say 100 or 1,000 times, you would get probably the most likely outcome. And one outcome is maybe appearing much more often than the others. And that's the most likely result. But it could be wrong, because it's probabilistic. So we see all of this quantum computing stuff is highly non-deterministic. And there will be more components later adding to the non-deterministic property. So you run the same experiment twice and you may get a different outcome. And once you measure, your experiment is actually over. That's why writing code for a quantum computer is actually tricky if you want to debug your code. Because with debugging, we are used to looking into states, but here, if you try to debug, the experiment is over. And there's another problem. In today's quantum computing, we largely deal with these super low representations. Like, we need to deal with the individual quantum gates. And there's much more than the NOT and the Harder-Matt gate. There are many more operations. And this is certainly a challenge, because you need to learn about quantum mechanics in order to build new quantum algorithms. Because in quantum algorithms, you want to eventually lead to a speed up, but you need to exploit quantum mechanical phenomena. If you look back to what computing looked like 60 years ago, or 70 years ago, you also had to look into individual bits and how to manipulate them, how to, connect which relay to each other. So this was also super low-level software development as such, because you had to look at the individual binary operations. And building large-scale algorithms was impossible. For that, we needed more abstraction layers, like more programming languages like, I don't know, assembly as a first abstraction layer, then Z or whatever, and today Python or Java. And I think in order for quantum computing to really evolve and have much more applications, we need to reach higher level abstractions that work. Because you as a software developer, you don't want to be thinking on that level. Rather, you want to use a more high level programming language that would compile this into low level. But this is one of the challenges for the coming years and decades. But you still need to know at least some foundations of quantum mechanics. I got a question here in the chat why it's called 0 and 1 ket. This comes from the so-called bra-ket notation, which is very common in the quantum world. So maybe just search for the bra-ket notation. And I'm also writing this again in the chat, bra-ket notation. if you want to read more. Now, we have seen different gates, like the Harder-Matt gate, the NOT gate, and you're wondering what other gates are out there. And can I use any possible matrix simply as a quantum gate? And it turns out only certain matrices that have a specific property are able to be such matrices. And I just need a moment to share do my screen share again, because the Zoom app refreshed. Screen share is coming now. The update just took a short moment. So, and we need to look a little bit more into matrices. And what we need are so-called unitary matrices. So these are matrices that have a specific property. And a unitary matrix, or a matrix U, is unitary if U times U, so U times itself, which isn't fully done yet because we have to apply once this operation here. This is pronounced as dagger, so U dagger. So U times U dagger must be the same as U dagger times U. And this needs to be I. And remember, I is the identity matrix. And the identity matrix is all 0 except its first diagonal, which is all 1. So U times U dagger must be the same as U dagger times U, and that's the identity matrix. And now you're wondering, what does this dagger mean? And the dagger is something that refers to the adjoint matrix. And an adjoint matrix looks the following. For, say, a 2 times 2 matrix. I have a 2 times 2 matrix which has entries A, B, C, and D. And I apply this dagger operation to it, and then I will get the adjoint of my original matrix. And it will look something like this. A, Z, B, and D. But I put these bars on top because this whole theory about adjoint matrices deals with complex numbers. Who of you remembers if I have a complex number and I put a bar on it with a complex number, what does that mean? If you have any suggestions, let me know. Oh, just wait. Yeah.
Is it the conjugate?
Yes, the conjugate. Just as a reminder, the conjugate is, say, I have just do it with an example for now. So I have a complex number which is 5 plus 2i, and its conjugate, that would be 5 minus 2i. So I change, or I flip the sign of the imaginary part. And if A, B, C, and D are complex numbers, then I have the conjugates of A, Z, B, and D. So I have all these conjugates, and I have also flipped B, and Z. So I have done the transpose and I apply the conjugate to each element. And we can try this out with an example that we all feel okay with conjugates. So the example would be the first entry is 6 minus 3i. Next entry is a 2, and 9i, and a minus 2 plus 4i. This is my matrix. And I want its adjoint, so I apply the dagger to it. And this is also your task now to apply the adjoint operation. So remember, we transpose it, plus we want the conjugate of every entry. And if you have a solution, send it to the chat. The first row is 6 plus 3i. And the student who sent this to the chat forgot the transpose because we are also transposing. So we would actually have the 9i here, but then minus 9i, because it's the conjugate. Then the 2 comes down here. The 2 doesn't change because it's only a real part. The last entry is minus 2 minus 4i. So now we know what the adjoint matrix is. And now we come back to our unitary matrices, because we've said if we multiply U times its adjoint, which is the same, and if it's the same as taking the adjoint times U, this must be the identity matrix. This is super important to quantum computing, and we will soon see why, but we first try an example about unitary matrices. So example, a unitary matrix. So we say we take the Harder-Matt gate from before, and the Harder-Matt gate, as you may remember, was 1, 1, 1, minus 1 with this constant factor. And I want to check if it's unitary. So remember, for unitary, U dagger times U must be the same as U times U dagger must be the identity matrix. For now, we only test this part, so U dagger times U. So this is my U. So I say dagger times U, which is 1 divided by the square root of 2, 1, 1, 1, minus 1. This is something you can try at home as your homework to do this multiplication, but what you will see when you do it, because it's finally just multiplying elements now, which you can try at home, we will actually get the identity matrix. And if you flip U and U dagger, you will also get this. So that means our Harder-Matt matrix is actually unitary. And before we also had the NOT gate. The NOT gate was 0, 1, 1, 0. And you're most welcome to check that this is also unitary. And all quantum logic gates that we want to use, they need to be unitary. And you're wondering, why is that the case? Superpositions are extremely important in quantum computing because I need to create superpositions in order to have parallelism. But sometimes I create in such a process unnecessary ones, and later I want to undo this just to reduce the superpositions that I have. And now if I have a gate U that does a certain manipulation, I want to be able to undo it. And if it's unitary, I can easily undo it. If it's not unitary, I cannot necessarily undo it. And what this refers to is actually the field of reversible computing. Reversible computing. And in quantum computing, reversible computing is super important. If you remember classic logic gates, so classic logic gates. So, for example, I have a NOT gate. That one is certainly undoable. Sorry, that one is certainly reversible because I feed in something and I flip it, and then I could just flip it again, and then it's undone. So in classic logic gates. But I have other classical logic gates, like, for example, an AND gate. I feed in two values, and I have an AND, and I'm unable to just undo this from the result, because I have the result, which is just one bit, and I'm unable to refer the two incoming bits from that one. So that one is not reversible. And the OR gate is also not reversible. Only the NOT gate in classic logic gates. And in quantum computing, I want all operations to be reversible. And that's why I require, when I now describe my logic gates, my quantum logic gates as matrices, that I only pick the ones that are unitary, so I'm able to undo them in order to reduce the superpositions later when necessary. Otherwise, I have unnecessarily many superpositions. This is most of the maths for today. I know this isn't that easy because what we're doing is complex linear algebra. We are using linear algebra, but we are doing this on complex numbers, which probably most of you have not done so far. And this is the maths, and now we'll talk a bit more about concrete quantum computers and how to program them. And then we'll look into algorithms that actually provide a speed up in terms of the complexity, because now we have all the low-level work done. I've said programming quantum computers is challenging. We have a very low abstraction level, plus we have these measurements which are non-deterministic. But there's one more problem that will further complicate the computations, and this is called decoherence. We want to separate a quantum system from the outside world, because if our quantum system starts to interact with the outside world, eventually it will decohere. What it means is it will lose its purity. So I will add noise if my quantum system interacts with its outside world. Now you think, well, it's perfectly isolated. This is actually not possible. And even if we could perfectly isolate it, then we wouldn't be able to manipulate it from outside anymore. Because from outside, I want to give instructions of how to manipulate the qubits. So there will always be some decoherence. If I shield the system very well from the outside world, then manipulations will be very difficult to do. But I have little decoherence. If I don't shield it well, I can easily manipulate it, but there will also be lots of decoherence, and I will lose the purity of my state. So all of these are challenges. And now I need concrete quantum computers that actually work. And for many decades, they were actually just pure theory. All of this was a theoretical framework. There were algorithms in the theoretical framework. But then someone needed to build actual quantum computers. There are universal quantum computers. For example, IBM does this. And then you have some universal quantum computers with maybe 50 qubits or something. And you wonder, is 50 qubits a lot or not? Well, it's actually not much that it works for real-world problems. So we need substantially more qubits. But if you add more qubits, you will also add decoherence as usual, or usually. And then you also need to address the decoherence. For example, there are some quantum computers that would use error correcting codes, but then you need even more qubits just for the error correction, while increasing the decoherence. So there are some cases you keep adding qubits, but you're not getting anything out of it because you just need to address the extra decoherence with more error correcting qubits. IBM uses a term that is called a quantum volume, so the number of qubits you can effectively use for computations. There are other architectures, like for example from D-Wave, what they have focused on are so-called quantum annealers, which comes from the branch of adiabatic quantum computing. In a quantum computing quiz, you would discuss all these different architectures, but it doesn't matter for now because it's just an overview of this course. And soon we actually want to look into algorithms. So how can you actually get started now with quantum computers? For many years, you had to use a simulator because quantum computers did not exist. So you had to use a simulator like QuizKit, for example, from IBM. That's one approach. The other approach is nowadays, you can run your code on a real quantum computer. What does a real quantum computer look like? Well, they are relatively big. Like this machine here is a D-Wave 2000Q that the vendor or the company D-Wave started selling a few years ago. Now they have other ones, but the D-Wave 2000Q, for example, has 2048 qubits. I told you the IBM architecture maybe has around 50. It's very important. You cannot compare a quantum annealer to a universal quantum computer. So the number of qubits here doesn't really allow us to make a comparison between architectures. And these qubits, they are made of niobium. And niobium is a metal. And now you wonder, how does a metal create superconductive effects in order that we are able to do quantum computing? If you cool niobium down to 15 millikelvin, so that's close to absolute zero, which is minus 273 dot something degrees Celsius, then niobium becomes superconductive. And you can actually create quantum effects on your chip. If you want to buy such a machine from D-Wave, you need to spend, I don't know, $15 million on it up front, as well as you need to spend lots of money on the cooling. Actually, most of this machine is just for the cooling. The actual chip is relatively small, so most actually just for the cooling, and the cooling may cost you a few more million per year. So it's expensive. What you can do instead is D-Wave runs some quantum computers on their own. You can sign up with them, and you can access a real quantum computer through the cloud. So they would give you some computing time on a real quantum computer for free. If you need more time, you can buy more time. And this was from a few years ago. What they offered was, and now it's even more evolved, they offered something like a Jupyter notebook in the D-Wave cloud, and you could implement your code using the D-Wave libraries, and eventually you could either run it in a simulator or on a real D-Wave quantum computer using your free minute of computations per month. I've run this computation, I think with some clustering or something, or some small demo, and eventually this took like 0.3 seconds on the quantum computer. So you don't need to invest 15 million up front, rather you can use something like that. This is not an advert for D-Wave. That you can do the same with IBM, or you can get an API token and you can access this from your local Jupyter notebook through the cloud. So there are lots of ways how to access such machines. And if you need more time, you need to buy more time. Now, what are the impacts of this on actual computing and on complexity? I want to start with Grover's algorithm. And Grover's algorithm addresses a so-called black box search. Black box search means we have some black box that we are unable to look into, and we can feed in an input. Concretely, n many different inputs over time, where n could be large. And I want to know which one is the right input so my black box returns true. And I don't know the logic of the black box. There's some magic in it, or almost magic. So I'm unable to look into it. It could be, you could see also the black box search as an optimization problem. One input is the right one, maybe the best solution to the optimization problem. And if I don't know how the black box look like, I need to try in classical computing each one in a row. Obviously, I could be lucky that my first input, say I have 1 million possible inputs, or let's say 1,000 inputs. For now, I have 1,000. No, 1 million is better. We have 1 million possible inputs, and maybe the first one I'm trying is actually the solution. And then the black box returns, yes, this is the solution. Then in the best case, it's obviously O of 1. In the worst case, it's O of n, because in the worst case, I need to try all possible n inputs, and maybe the last one is actually the solution. In average, I need to try n half many, but n half with the O framework is still O of n. So this is what classical computing looks like. And now comes the pure surprise when I use a quantum computer and the so-called Grover's algorithm. I will get a massive speed up of the black box search. Using Grover's algorithm, I will need approximately pi divided by 4 times square root of n many possible inputs to find the optimal one. Or say not inputs, but checks. Square root of n times pi divided by 4 many checks. So not O of n, but this is actually O of square root of n. Are you surprised that using quantum mechanics, I can massively speed up something like a black box search? If you find this curious how this could work and you want to learn more, or you're surprised, maybe thumbs up. If this is something that doesn't surprise you, maybe thumbs down. We are unable today to discuss, obviously, Grover's algorithm. You can look it up, and there's lots of resources in it on the internet. I'm providing a few more URLs very soon. So Grover's algorithm gives us a squared speedup. The only problem is now all of this is highly non-deterministic because we have measurements that are uncertain. We have decoherence and lots of other challenges. So the Grover's algorithm only finds the solution in this O of square root of n with a high probability. But maybe it's the wrong one. But once I have this solution that the Grover's algorithm returns, I can just put it into the black box and see if it's actually the solution or not. The black box says, yes, this input is the solution, I'm done. If it says no, I need to run the same experiment again because it's non-deterministic. And I may get a different candidate, and this different candidate I can put as an input again into the black box, and the black box would say yes or no. And in the worst case, sometimes I have to do a few attempts of this. But still, because this is O of square root of n, and if you make n big, like 1 million or 1 trillion, then square root of n really leads to a speed up. And the good news is that Grover's algorithm is also sometimes called a quantum search. And you can use this to all sorts of optimization problems to get a squared speedup. The challenge today is implementing this for large-scale problems on a real quantum computer, because we don't have sufficiently large quantum computers yet. This is something we hope for in the coming years and decades, but there are lots of challenges in physics to actually build something like this that keeps decoherence low. But it's a highly generic algorithm for all sorts of problems. Now, it's a squared speedup. Now, some people would say it's only a squared speedup because when I explained you earlier, when we started with this topic, and I said what happens if you have 10 qubits combined, how many possible states we're looking into at the same time, and hopefully we could get even an exponential speedup. And there's a second quantum algorithm, which is called Shor's algorithm. And Shor's algorithm addresses a totally different problem. It addresses integer factorization. So you have n, which is a large integer, and we want to know P and Q. So P and Q are prime numbers, and the product of P and Q would give us n. So we want to decompose n into its prime factors. This is a problem for which you need exponentially much time, or almost exponentially much time if you make some assumptions. And because this is so difficult to do, integer factorization for a large n, that's the backbone of today's encryption. Now comes Shor's algorithm, and Shor's algorithm gives us an almost exponential speed up of prime factor decomposition. The Shor's algorithm runs in such a quite one that looks ugly here, O of e to the whatever. And the Shor's algorithm gives us an almost exponential speed up for finding the prime factor or the prime factors of an integer. And this would allow us to massively target today's encryption. Once we have larger quantum computers available, probably they can be used extremely well for cracking encryption. That's why there is lots of work currently going on. I'm sorry, I made one mistake. In classical computing, this is the complexity. So in classical computing, not of Shor's, for Shor's, this is the complexity. And this is, so this here is the high complexity for the classical, so the naive or the general number field sieve, which is not the naive one, but it makes some assumptions, but still this is extremely slow. And the Shor's algorithm runs in polynomial time and gives us a much better speed. So this is a bad one, and this is a good one. This is of the Shor's algorithm. And Shor's algorithm gives us an almost exponential speed up. And once this is available on large-scale quantum computers, this will probably end today's encryption. And that's why numerous companies are working on post-quantum encryption, so with new algorithms that cannot be cracked by a quantum computer efficiently. This is something that is going on. There is standardization going on and all sorts of work, so that once such larger quantum computers are available, that we are safe, that we have switched to new encryption methods. No one really knows when that day is coming. I don't think it will happen that soon, because building such much larger quantum computers with much more qubits that we can effectively also use, that's a huge challenge. But we don't know, so it's something we need to observe, and that's why companies like Google and IBM, they're massively working on this to build the future of encryption that is quantum safe. And it's a very exciting time, especially for those of you who are in our cybersecurity program. Now, this was the overview of quantum computing. You've seen quantum computing is quite low level right now. You've seen two algorithms. There are some more in the literature, but not that many that work on real-world problems, because building your own quantum algorithm is tough, because you need to know about quantum mechanical phenomena, and you need to take advantage of them in the way so you're actually able to solve a real computational problem in a much better complexity class. If you're curious and want to learn more, there are lots of resources here. A very good website is called quantum.country. These are very interactive essays on quantum computing, and you can try them. You learn something, there are some quizzes, and overall, this provides you with a very good introduction to quantum mechanics, then to quantum computing, and then, for example, to the Grover algorithm, which is the black box search. These additional readings here, they are obviously not relevant towards the exam, but everything we have done up to here is obviously relevant for the exam. You don't need to know how Grover's or Shor's work, because we haven't discussed them, but you need to know about what they address and with what complexity they come and what problem they solve and which speed up they provide, plus all the maths from before. If you want to read about this, check the extra resources. And we're now coming to an end in this course. I'll say a few closing words, and then I say a little bit more about the coursework and the exam that will take place in a couple of weeks. So most of you are in the second semester of your undergrad program, like computer science or cybersecurity. There are some other students, obviously. And something you also need to bear in mind is that there will be more courses in the future, and you will deal again with me if you are in one of the AI programs. I teach multiple courses in the 2 undergraduate programs in AI, both in the German and English language programs. In the 4th semester, I teach computer vision. That's where you will meet me again. Some cybersecurity students take this one here as an elective. Then in the 6th semester, I teach big data. I also supervise the AI project. And once you do your internship in the 5th semester, there is an accompanying course that is called Innovation Management for AI, in which we address management issues and how you can actually commercialize artificial intelligence in a company, while the other courses are technical. So big data is about handling large amounts of data and learning on large amounts of data. Computer vision is understanding images or videos using AI. And the AI project is a bigger project we do with companies. These are the mandatory courses in our AI programs. And I also teach an elective that is called quantum computing, which I always teach in the winter term, in which we discuss quantum computing for the whole semester. And there are seminar presentations at the end of the term where students present some paper or some problem around or some algorithm around quantum computing. So if you have enjoyed this intro to quantum computing, you can learn more in our quantum computing elective that I teach together with Professor Kuhnhardt. And for those of you who are in the AI undergrad programs, there are obviously much more courses on AI that you will deal with, like AI programming. There will be the AI seminar, assistant systems, autonomous robots, deep learning, machine learning, natural language processing, and so forth. But I'm not involved in these courses. They are taught by others. I hope you have enjoyed this course and learned a lot about algorithms and data structures. Don't forget the coursework. So some students have already started submitting and I'm sorry, this is the wrong coursework sheet because I looked into last year's exams. So I opened the wrong coursework sheet. This is obviously this year's coursework sheet. And don't forget your mandatory problem and your exam bonus problem. The second one is obviously if you wish, but the mandatory problem is mandatory, so you can sit the exam. You can find these sheets in Nextcloud. Some students have already submitted the mandatory problem. And this was our last lecture. We have labs for a few more weeks, as I have announced. We have labs until the deadline. So we have 2 more weeks of labs, which is, so today is the 14th, so the 21st and 28th. The submission deadlines in the coursework are the 29th. And before the exam, we will meet again. We will meet online here on the 5th of July, because you have seen my announcement in iLearn, and we will discuss last year's exam. Last year's exam is something you find in my Nextcloud, and my exams always look the following. You have 90 minutes, and there are 3 big problems. Each problem carries 25 points, and you're supposed to pick 2 of these problems. So you have a choice. So in total, you can score up to 50 points. And in my Nextcloud, you also see how I convert points into a mark. If you do the exam bonus problem successfully, you will get 5 points on top. If you have enough time, you can work on a 3rd problem, but only the best 2 problems will count. So if you do all 3, the best 2 count. So focus on 2. Don't scatter your efforts among these 3 problems. rather focus on 2. And if you have time left, maybe work on the 3rd one. So you can pick. I think it's a good choice for you. This is a system I saw when I did my master's in England at Imperial College. There, I think it was something like 3 out of 4 problems. And I asked what would happen if I did all 4 problems. And then they said the worst 3 would count, not the best 3. But here I'm friendly, so it's 3 problems and you pick 2. And if you really have time to do a 3rd problem, then the best 2 will count. And the exam bonus will also help you to improve your mark. You can take a look at last year's exam. The first problem addressed something around linked lists. You had to implement some algorithms around linked lists. The second problem was about decision trees, and plus something about complexity a little bit. And the third problem addressed the fast matrix multiplication recurrence relation, plus a little bit on quantum computing. I advise you to be familiar with the whole content of the course and prepare everything, because you don't know what the problems will be looking like this year. And this is the exam from last summer that we will discuss together on July the 5th at the usual times of 3:45. We'll meet here in Zoom. That meeting will not be recorded, and you're advised to prepare your solutions for last year's exam, because I will not provide any solutions upfront in our discussion. However, you can present your solutions and I'll give feedback and then maybe explain how I would have solved it. I will not pass, or I will not provide any solutions on my own upfront, because otherwise you will not be preparing for the exam properly. Some students every week also talk to me in the lab because they have worked on past exams. You can always ask me in the lab about past exams. I'll be happy to comment on your solutions and give you insights, maybe show you how I have solved it, but I will never provide this upfront or share it digitally. Otherwise, no one will actually really study this anymore. This year's exam will look the same, that there are 3 problems. There's only one small change. It turned out last year there were quite a lot of students, or some students, maybe not quite a lot, but some, they somehow struggled with an exam in English, and they caused lots of arguments during the term. That's why starting this year, the exam will be in both languages. And last year for the exam, I provided a second sheet with the questions translated. This year, the sheet will look a little bit different. So this was the resit exam from the winter semester. And from the winter from that resit exam, you see the structure is still the same, but everything is provided in English as well as in German. So the front page is now 2 pages. And the problem here is I first pose the question in English and then in German. So you don't need to flip back and forth, going to the last page, trying to find the translation. The translation is in here. Ideally, you would be answering the questions in English, because it will be probably most easy for you, because we have done this course in English. However, if you really wish, you can answer the questions in German or partially in English, German, as you wish. And that's why the translation of the questions are here. So this is what the exam last year for the resit looked like. And this year's exam will look the same. We still have 3 problems. You pick 2 out of 3, but you will have the question always in English and German. And the EN part is English, DE is a German part. I saw there was a question here in the chat, so just need to check it. There is a question about the coursework. So the coursework is, I require you to submit, it's very important, always submit an HTML export of your Jupyter Notebook. Not the Jupyter Notebook, because I don't want to be running this, but you can save your Jupyter Notebook as an HTML export. And you should upload this one. If you upload supplementary files, like for the mandatory problem, the text files you have used for finding patterns, you can upload them as well. You can, if they're not too long, you can put them directly in the HTML export as well. But I largely care about your HTML export of the notebook, and maybe I'll be looking at the text files. But if your files are too big, like 100 pages, don't put this in the report. Just upload this as a supplementary file. And you should ideally do multiple tests. So multiple texts, multiple patterns, and try all those algorithms on them and see if you see some behavior, maybe for which data sets and which patterns the one algorithm would be preferable, and for which other issues the other algorithm would be preferable. Hope this addressed your question. Are there any questions also about preparing for the exam? Because today is our last lecture, and we'll only meet in 3 weeks to discuss last year's exam. If there are any questions, go ahead now. Otherwise, I'm also available in the lab for the coming weeks, where I'm on site and online at the same time, as well as you can always get in touch by email if there are any questions. So there are no more questions. So I wish you all the best for preparing for the exam. What we have done in this course is key to your future career, because you will need algorithms and data structures for the rest of your career. Especially, you need to know how to build efficient ones. And I think you have now we've done the groundwork for you in order to also explore more advanced algorithms and data structures. Make sure you revise everything, and let me know if there are any questions in the lab. And I wish you a good weekend.